let me show you some uses of the behind operator. Behind is a compositional operator, and I have a little trick to explore what compositional operators do. I define some helper functions that are ambivalent, and all they do is to strand their name with their arguments. Okay, with this, we can now actually create the composition and give it a symbolic argument. And we can see that the monadic form of the derived function f behind g takes the right argument, applies f to it, and uses that as the left argument to g. If we insert a left argument, we can see that f is now applied to the left argument, and then we give that as left argument to g. So, in a sense, f is taken from right next to g and thrown behind the left argument and applied there. And if there isn't any left argument, well, then we take the right argument and use that as left argument for it too. Let me give you some examples of how this can actually be useful. So let's say we have some numbers. And we want to know which one of them are equal to the first one of them. So we can use this pattern. We want to apply the function first to the argument and then compare to the argument itself. First, behind, equal. We can see how essential this function, this operator is by what kind of description we need to insert into a phrase using these function names. We want to find where the first equals. So there's really nothing to say for this operator. It's that fundamental. Here's some character vectors. This one, the characters are unique. This one, not, because they're two L's. Now we can check if the unique matches for each one of them. The unique matches. Again, nothing there to say. It doesn't have to be just comparisons. Here's a Boolean mask. And let's say we want to overlay this mask with itself. So we want to find out where the reverse and itself. That's just that one element. We could also do the reverse or itself. Sometimes when you have, for example, points, but we'll just use x, y, and z here, we want to connect the tail to the beginning. So this is the last element, and we want the last catenated. We can also use this for arithmetic. Here's some numbers, and this function finds if they're even or odd, or the parity. If we want to adjust all the odd ones by adding 1 to them, then we want the parity added. And that gives us just even numbers. This function finds out which numbers are greater than 3. And we can use that to compress or filter. So the 3 less than filters. Some of the functions we can derive using behind are even useful as the filtering function. So let's say we have some strange numbers like these. We can find out where the floor equals, that is, those that are integers, and the integers filter. We extract all the integers. Here's some words. If the reverse matches, then we've got ourselves a palindrome, which means that the palindromeness filters extracts just the palindromes. This is the classic idiom for the average. The average is less than gives us a mask of those numbers that are greater than average. The greater than averageness can then be used to filter. All of these uses were of the monadic form of the derived function. Let's look at some dyadic ones as well. I'm sure we've all had this issue. This doesn't work, because to look for a single element in a vector of elements, we have to enclose the left argument. So we can sort of fix the element of function by making it enclose its left argument first. This is sort of a new primitive, so to say, a derived primitive that looks up just a single thing. Similarly, the index function has the problem that if we want to pick out individual elements, we have to enclose the left argument. So we can fix this index function into a selection function using enclose behind. System functions like NPUT need to have the data that needs to be written to file enclosed as well. Otherwise, it can't tell if we're trying to have some data and also specify an encoding. So we can fix the system function by making it enclose its left argument. We can also use it inline. So let's say we are constructing some texts with a template here, and we have a number that we want to insert. It would usually be from a variable or some formula. But we need to format it first. So we want to make sure that this catenation formats its left argument. Let's say we have a polynomial which is x squared plus 2. We can represent this as 1 times x squared plus 0 times x plus 2. And we have the function decode to evaluate this polynomial for a single value. But it doesn't quite work if we want to evaluate it for 2 separate values, because it will want to pair up the numbers on the left with the numbers on the right. Instead, we have to supply our left argument as a column. So we make a fixed version of the decode function by doing a table behind. this function is not just a normal reshape, but rather the shape reshapes. So here is an array, and we take its shape and make it reshape something else. We have the index function, index of function, but there's no index of function that counts from the rear, looking at the offset from the end to the last element of this value. We can construct that. So this is a reverse index of. So we can see the A was at the first position and the B was at the third position. If we have a Boolean mask, we have the where function to convert it into indices. Notice that if they're trailing zeros, we don't get this information along in the result. So where is sort of lossy, and there's a piece of information that we need in order to go the other direction, which is the length of the vector. That doesn't exist as a primitive, but we can easily make it. We specify the length, which is 8, and then we want to find all the indices that are in this list. But of course 8 isn't the indices. We need to convert the number 8 into its indices first. People sometimes speak about compress as a filtering function. I did that right before. But really, that's an ambiguous term. Because are we filtering in or filtering out? Does this mask indicate which elements we want to keep or which ones we want to discard? Well, compress does indicate which ones we want to keep. But there's no primitive for those we want to discard. That would be not behind compress. Let's look at the take function. We can also take from the rear with negative numbers. But there's really a complementary primitive, which would be the primitive that takes from the rear, even when you give it a positive left argument. We can implement that as negate before take, or behind take. Now, how is this useful? Since we can always use negative numbers. Well, let's say that we want to take the first and last 3. We can do this with a fork. The first 3 catenated to the last 3. There are even some ambivalent functions we can write with behind. So here's a fancy sort function. We have the indexing function, and we know that we need to enclose the left argument in order for it to select the right thing. Instead of enclosing the left argument as is, or enclosing the right argument, which wouldn't make much sense, we can enclose the grade. If we then try to sort some normal data, we can see that works just fine. What happened here? Well, we have a monadic application of a function derived from behind. So we take the argument, apply this function on it, which is enclose of the grade. That's exactly what we need for the indexing function to sort. But what if we have a list of names? And we want to sort them by age. Well, that works just fine. Why? Because we have the left argument being preprocessed by this. So we grade the left argument, which tells us how to reorder the right argument, enclose it in preparation for the indexing function, and finally reorder the right argument with that. Here's a fancy splitting function. It's reminiscent of a very well-known fork. The difference or unequal partitions the right argument, but we've thrown in this first behind. Here's a text that I've prepared, and if we use the split function on the text, then let's see, we got the fork, and the right tag here just gives us the argument. This function is then applied to the argument as well. It's using behind, so we take the argument, take the first element, that's the comma, and compare that to the whole thing. And that gives us the splitting mask for partition. So this function splits on the first character. If we give it a left argument of, say, a space, it splits on spaces instead. What happened? Well, we've got this fork still, but now we've got a left argument. This gives us the text as before. Here, this is unequal, where we pre-process the left argument to the first. Well, we gave it a single space, and the first of space, that's just still a space. So we compare space to the entire text, and that gives us the partitioning mask. So these are a bunch of uses of the behind operator. I'm sure you can come up with many more.